Have you ever seen an exponential equation you just couldn't seem to crack? Keep watching. I've got 3 examples to get you up and running. So, hey sports fans, it's Planet Numeracy and I'm Mark Noldy, your personal math coach. I've been teaching students for almost 25 years, and I always know when they're going to struggle. But when it comes to exponentials, you gotta know there is no substitute for rudimentary arithmetic skills. You know, the times tables, your perfect squares, your perfect cubes, things of that nature. So let's get started. All right, friends, here's our first example. We're looking at 4 to the x plus 2 to the 1 plus 2x equals 50. So we have to solve for this exponent. So we're going to eventually be doing a logarithm, taking a log on both sides. But what I see here is 4 is 2 squared. So I like that. So I'm going to replace 4 here with 2 squared. Right? And that's 2 squared to the x power plus 2. Oh, what can I do here? I could do a 2 to the 1 times 2 to the 2x. What's that? Are we allowed to do that? Yeah, sure we are. Think back to when you first learned, say, exponent rules. If you were multiplying and you had like bases, you would simplify that by keeping the base and adding the exponents. So 3 plus 5 here is 8. Well, look over here. This is the same bases. If I was multiplying these, I would add the exponents 1 plus 2x. So we're allowed to use that in reverse as well. So that comes in handy. All right, let's keep on going. We have, let's say I'm going to use the power rule. I'm going to switch my colors first. I'm going to use the power rule and say that is 2 to the 2x plus 2 times 2 to the 2x. So that's why I was excited about this 4 being up here, because now I have 2 to the 2x. I have this same thing in both terms. So I can factor 2 to the 2x out of this term and 2 to the 2x out of this term. So let's do that. 2 to the 2x. Now be careful here. There's still a 1 remaining in here. In other words, if I went backwards, this is what would be happening. 2 to the 2x times 1, that's 2 to the 2x. 2 to the 2x times 2, that's 2 times 2 to the 2x. So a common mistake I will see students make is they'll forget to put this 1 in here. So I try to always remind them of that, and usually throw a couple of these on a quiz as well. So 1 plus 2, that ends up being 3. So 3 times 2 to the 2x equals 50. And then we would divide both sides by 3, because I want to isolate the term that has the x in it, this piece right here. So now I can go ahead and take the log of both sides or natural log of both sides. It doesn't really matter, but when I take the whether it's log or natural log, that releases the exponent to the front here. And I'm also going to have to do the same thing on the other side. So the natural log of 50 divided by 3. And then to solve for x, I'm going to have to divide by 2 and natural log of 2. So x equals the natural log of, need a little bit more space here, 50 divided by 3 all over 2 times the natural log of 2. So that's your exact answer. Sometimes a book will say come up with a decimal approximation. I looked at my calculator here. It's about 2.029. But a lot of times I tell students just to leave it here. we only have 45-minute periods, so if they're working on a quiz or a test, they don't have a whole lot of time to do this with. So let's look at the next example. Okay, looking at example number 2 here. A lot of these, like I said, really hinges on a student's ability to know their perfect squares and perfect cubes, especially the ones that get used more frequently. So what I'm looking at here is I like that 125 is 5 cubed to the x. And why do I like that? Because I see a 5 to the 3x here. 3x, 3x. So this is very similar to the last example. So we're going to go ahead and write this as 5 to the 3x times 5 to the 1. Again, remember if we had, n to the 4th times n to the 3rd, that would be n to the 7th. So you keep the base and you add the 2 exponents to get 7. So if I went backwards here, 3x plus 1, I'd keep the base 5 and add the exponents 3x plus 1. So that's how we kind of deal with those. So that's if you just take that away from this, this is going to help you with many homework problems and even test problems. So 5 to the 3x. Okay, use the power rule again here. Then I have 5 to the 3x times 5 equals 200. All right, so similar to before, I'm going to factor out a 5 to the 3x. But what's left over in parentheses is 1 plus 5. So don't forget that 1. So I've shown you 2 examples here. This is a very common mistake among students. So just double check it out again here. When you multiply 5 times 3x to 5 to the 3x times 1, it's just 5 to the 3x. When I multiply 5 to the 3x times 5, it's 5 to the 3x times 5. So we're using like a lot of rules of logarithms and even rules of exponents here. Not rules of logarithms. These are exponents. But we're going to take logarithm here just to solve this. So the first thing I want to do is get rid of this 1 plus 5. 1 plus 5 is 6. So I'm going to divide both sides by 6. We can do that, right? So 5 to the 3x equals 200 divided by 6. And that reduces, I guess. I could say that's 5 to the 3x equals 100 over 3. In my next step, I will go ahead and take the natural log of both sides. So I'd have 3x, or you could take the log, it doesn't really matter, of 5 equals, you just have to do the same on both sides. I don't know why I learned how to use natural log early on, probably because the button was easier to find on my calculator when I was in school. In any event, took the natural log of both sides, and that releases this exponent. Comes out here to the front, natural log of 5. So I'm going to divide both sides. I want to solve for x. So I'm going to divide both sides by 3 ln of 5. So x equals the natural log of, and you might write them this way as well, 100 thirds divided by 3. Oops, I switched my erasing. Divided by 3 times the natural log of 5. And there may be parentheses around that. So again, this is an exact answer, right? It's not a decimal answer. Doesn't really make sense to most people. So for that reason, a lot of times people will simplify this. Not simplify it, but come up with a decimal approximation for it. So decimal approximation, exact answer. All right, this one is looks a lot like a quadratic, but what we're going to do is use a u substitution. So I'm going to substitute in this. It would be really nice if e to the x, could I say let e to the x equal, I don't know, u. So that would become u squared minus 3u plus 2 equals 0. So this is much easier looking to factor. So we need to factor this to solve it. We like to use the zero product property. So we have factors of positive 2 that add up to negative 3, and those would be negative 2 and negative 1. So checking that, negative 2 times negative 1, that's 2, and negative 2 plus negative 1 is our negative 3. So if this times that equals 0, either this equals 0 or that equals 0. So we have u equals 2 or u equals 1. Now, don't forget, what is u? U, we said, was e to the x. So we just solved this and we said, well, e to the x is 2 or e to the x is 1. So on the left-hand side here, e to the x equals 2. If I took the natural log of both sides, I would just have x equals natural log of 2. Here, any number to the 0 equals 1, right? This is just a number, right? 2.718, so on, so on, so on. So x would have to be 0 here. So x equals 0. So we have two solutions. So x equals the natural log of 2, which would work in this equation, and x equals 0, which would work in this equation. So there you have it. 3 good examples that are tougher than usual, tougher than usual exponential equations. One of them that was in the form of a quadratic here, but hopefully they get some insight from this, and you'll know how to tackle some of the problems that you're going to see in your pre-calc class going forward. I hope you got value. Go ahead, please hit the like button and subscribe. This helps people who might be searching for the same content to find it. Also remember, math's not a spectator sport. The only way to learn math is to do math.